All right.
Okay, so it is my pleasure to introduce our third speaker, the last one of the session. His name is Bojian Yin, sorry. He's doing his PhD with Sander Bohte, a big name in spiking neural networks, and he does research on SNN training and with a special emphasis on the neuronal dynamics. We are looking forward to your talk, Bojian.
Okay. Hi, team. Yeah. Thanks for giving me the chance to present our current work, training dynamic spiking neural networks by forward propagation through time. This project has been done together with Federico Corradi and Sander Bohte. So in the title, we figure out I have two things: dynamic spiking neural networks, how dynamic it can be, and the second is the forward propagation through time. How can we using these things to train our spiking neural network? So thanks for the previous talks. They are very informative and interesting. So people now they already know what is spiking neural networks and how it works. So, but I would like to briefly go through, in my view, how the spiking neural networks works. So we have training of neurons in our brain, and these neurons they communicate with each other using binaural spikes, and sparsely connected using synapse. Once a spike came approaching the synapse, a series of the biochemical reaction will raising up the membrane potential of this neuron, and the membrane potential will be transferred along in the neurons. During the transformation of the membrane potential, the membrane potential will be leaky, and this leaky property has been determined by many parameters. For example, the type of the neuron, the life cycle of the neuron, or the neuron behaviors, or it also depends on you are sleeping or not. So our neurons is far more complex than what we can imagine. And some people, they also found they may have some quantum mechanism inside. We do not want to know this deep, but we can simplify these mechanisms for calculation to know how can we generate the spiking neural networks just based on a simple leaky, integrate, and fire neurons, where the time constant tau is used to dominate the leaky property of the membrane potential. So the spikes come from the different synapses at a different time, and the membrane potential will be accumulated and involved in this procedure. Once the membrane potential reaches the threshold, the neuron can emit a spike and send it out to the next neuron and reset the membrane potential. So we can easily convert this mechanism into a computational manner. So we have the computational figure in this way, where in the leaf neuron, the membrane potential shows in the self-recurrency. It's involved along with the input, along with the time, but the time constant has been controlled by its time constant tau m. In previous papers, people use them as a fixed term or learnable term, but in our brain, it's far more dynamic. And how can we make them more dynamic? And this module of the spiking neurons is equivalent to what we know is vanilla recurrent neurons, where the hidden states is also involved along with the time. But the involving of the hidden states is determined by the recurrent connections, which is the big matrix. But for now, we already know that such a spiking neuron is recurrent neurons, which much more complex internal circuits. So if we know that the spiking neural networks is a recurrent neural network, the answer of how to training such kind of network is very obvious and clear. We can easily using the back propagation through time, which are widely using to training recurrent neural networks to training our spiking neural networks with help of the theoretical gradients. In last several years, it already showed very good results in a bunch of tasks, like image classification, sequence classification, in some control tasks, and even in something about much more complex. But when we're using the BPTT for the spiking neural network training, we may facing two main problems. First, conceptually, the BPTT works by unfolding the time steps to calculate the gradient. So the gradient calculation requires to store all the hidden states. Imagine if you have super long sequence, the memory you caused on your training will be linearly increasing, and it cannot be feasible to training such a spiking neural network on a single GPU. But our brain is much more energy efficient. We do not need such a big RAM to train our networks. The second problem is because the existence of the sum of the products in the temporal dimension gradient calculation. They may result in the gradient vanishing and explosion. And these two problems is much more serious in the training of the spiking neural networks, because first, the spiking neuron, we have more hidden states. We have membrane potential, spikes, and maybe adaptation circuits and other things we want to add. And the second problem is we have much more complex internal circuits, which may also increase in the risk of the gradient vanishing and explosion. So if we want to training a deeper spiking neural networks on a longer sequence for more complex tasks, we need to looking for a more effective and efficient learning algorithms which able to train our spiking neural network in an online manner. But we all know that currently such online learning algorithms are limited to training shallow networks, single layers or two layers. But how can we go deep? So in 2021, the Cal introduced the algorithm forward propagation through time to training recurrent neural networks. Here we want to explore, can we using this algorithm to train our spiking neural networks? So in comparison with the BPTT, if you check the computational figure on the right side, you only see the gradient calculation along the spatial dimension. There is no gradient has been calculated along the temporal dimension. So how the network can learn the temporal information without the gradient calculation along the time? So in their paper, they introduced the synaptic weights with synaptic trace for each weight, and these traces are used to store all the past loss summarizations. At every time steps, when the network wants to update the parameter, they may extract the loss information from the synaptic trace and feed it into the dynamic regulators. Then the network can only using the BP to learn both spatial and temporal patterns in the network updates. So actually, for every time steps, we have our loss has two components. First is instantaneous loss, our prediction loss. Second is regularizer loss. We call dynamic regularization loss, which determines how much we want to learn from the previous history. So with this kind of mechanism, we can training such a kind of recurrent neural network without store the hidden states. We just need to extract the historical information from the trees instead of store them. So with the help of this mechanism, which allows us to training large spiking neural networks with less GPU cost, so it also allows us to training the network on longer sequence. The second thing we got for free is, if you check the computational figure, you can say, because there is no gradient calculation, along with the time. So yeah, okay, you're back. So there is no gradient calculation along with the time. So the computational figure is much more clear, which we can say the gradient calculation is more robust. So it's much more friendly for our spiking neural networks because the surrogate gradient is approximation of the true gradients. So here we try to explain more details about these algorithms because the limit of time, if you want to know more, you can email me or contact me. I would like to share my understanding of these algorithms. But basically, the networks works in this manner. For every time steps, when you want to update the network, you have instantaneous loss and regularizer loss. You update your network based on this loss, and you can base the current loss and the new weight to update your traces. And these traces are used to store the historical information. To make our FPT works better, we introduce a liquid time-constant spiking neural networks with dynamic gating. In comparison with the traditional leaf neurons, where the time constant is just a fixed number, it can be initialized and trained. But here, we want the neuron can determine the time constant by the input and the neuron state itself. So we introduce the liquid time constant, where the time constant has been calculated based on both inputs and current neuron states. So it's played a role like kind of a gating mechanism in the time constant calculation. So it's play a role more like the glue neural networks. It gives the spiking neurons more dynamic. So we want to verify our idea. We're using the adding task as a toy task to verify our LTC neurons and FPTT. So In the adding task, we have two-dimensional inputs. The first dimension is a floating number from 0 to 1, and the second dimension is a binary vectors with only two ones. It may locate two elements. We want to add them up at the end. So we take the sequence with 1000 time steps and using the BPTT with LSTM as a baseline performance. So when we train our traditional adaptive spiking recurrent neural network and the liquid time-constant spiking neural networks with BPTT, they converge to the same level as baseline performance. But when we're using our liquid time-constant trained with FPTT, the network converges to near zero performance. It performs super good. After we verify our idea, we want to say how far we can go. Can we really gaining such kind of memory efficiency on the training? So we move our eyes on the DVS-gesture datasets. It has 11 gestures, and for each sample in the dataset is 1 second of the action captured by DVS camera. So based on the different frequency unsampling frequencies, we can convert these videos into different lengths of the sequence from 20 frames to 1000 frames. For this kind of task, we're using a shallow network to verify the memory use. So here we're using BPTT and FPTT to training different kind of neural networks. You can see that for all the neural networks trained using BPTT are failed to train them on 1000 frames because it's out of the memory on these shallow networks. And the second, you can also facing there is a performance decay when we have longer sequence, but the performance of both adaptive spiking recurrent neural network and the liquid time-constant spiking neural networks is quite stable, and they can even get better performance on longer sequence for the liquid time-constant spiking neural networks. We show the accuracies. We want to say, do we really saving the training memory? Here, we make the plot of the memory cost on the training. But we figure out that for both BPTT and FPTT, the memory use are both increased. It's not what we expect. We want the FPTT only using constant amount of memory. But why it happened? Finally, we figure out because when we unsampling the data using different frequencies, the data sets itself also become larger and larger. So we're using another task to verify this. We're using the rate-coded MNIST, where the input dataset is a fixed size, but you can generate any long sequence you want. So in this experiment, we can easily say that the amount of the memory required for BPTT to train a spiking neural network is linear with the length of the inputs, and that of the FPTT, it is constant. So it saves a lot of memory. Maybe we can training a deeper neural networks. So here we compared our networks with several online learning baseline models, but we are using deeper neural networks. So we can easily outperform the other online SN learning algorithms. And we also compare our performance with the offline SOTA numbers trained using BPTT. Our networks and algorithms together could be achieve or exceed the near offline accuracies. So with this kind of high accuracy and improve the memory efficiency, we want to go one step further. So we move our eyes to the object detection task, the spiking YOLO. There have several papers already been done based on the conversion, but in the conversion, they have two problems. The first is like, for the conversion, the simulation time is quite long. The network requires 100 to 1000 time steps. And the second problem, the sparsity of the network cannot be guaranteed. So with the based on the improvement on the FPTT, now we can train a spiking neural network to do this task from scratch. So our network are based on the tiny YOLO V4 architecture with 21 convolution layers, about 6.2 million neurons with 14 million parameters. The network has been trained on 4 to 8 frames, and the training memory with FPTT is about 14 gigabits. So you can imagine if you want to train such kind of task on BPTT, maybe you need 4 or 8 GPUs, but for here, we just need a single GPU. And our networks achieved the new SOTA on the Pascal VOC datasets. So because we know that our networks only takes 4 or 8 frames to draw the bounding box for this task. And in the video, they have no big difference in the nearby frames. So we can create a demo for that. And yeah, if we have time, finally, I can show you the demo. But here I can conclude in this paper, we introduce the forward propagation through time for the spiking neural network training. which shows we can use constant amount of memory to train any length of the sequence than BPTT. We also introduced the liquid time-constant spiking neural networks, which gives more dynamic for the spiking neurons. And together, we illustrate that our liquid time-constant spiking neural networks with the forward propagation through time are able to conduct online learning of a large spiking neural module on a longer sequence with the guarantee of the high performance and even with benefits of the constant training memories. If you want to know more, welcome to contact me. But here I can show you a small demo of the YOLO architecture. And I turned this into the real speed. So here is a wheel of arms time. You can see that our network running on the real videos, the 4K videos, is also quite good. But the bounding box is not that stable. But with the further optimization, it can be done. That's it. Thank you, Tim. Any questions? Yeah.
Thank you very much, Bojian. Very, very cool talk. Very cool talk. Yes, I've seen that we have two questions.
Yeah.
First one by Thomas Novotny. How does FPTT relate to EPROP, which is also a forward rule based on eligibility traces?
It's a super good question, because when we into this field to do the online learning, we always need to compare with the EPROP. The first thing we want to mention is for now, the EPROP only applied on the shallow neural networks. And this network, we are local in time, and we are be able to train in deeper neural networks. But we also believe that the EPROP can be expanded to training a deeper neural network. But I think they are totally different. For the FPTT, we require the label for every time steps or for every truncations. And we are using kind of common filters, try to make the network, try to recreate the direction of the weight optimizations. So it's different from the EPROP. It's more close as a variant of the BP instead of BPTT. I hope this can answer the problem. If not, welcome to send me an email. Yeah.
I think it does. We have another question by Jan Finkbeiner. Just to make sure I understood you correctly, with FPTT, you don't do any gradient computation across time, purely in space. Meaning you can get away with not doing temporal credit assignment at all. Is that a feature of the additional term in the learning rule or of the LTC neuron? I think you solve the temporal credit assignment, don't you?
Yeah, it's a kind of solving the temporal credit assignment, because they are using, they store the historical information with approximator of the future laws and the gradient. Then based on the mathematical works, you can convert this kind of traces information into the regulator laws. Then you can just based on BP, which do not based on the tracing back, but you take the historical information already out of the synaptic traces. And for the LTC neurons, because at the beginning we want it to work for the traditional adaptive spiking neurons, it doesn't perform super well. So in the adding task, it doesn't really converge. So we figure out that FPTT performs much better with the gating mechanism. So we introduced the LTC neurons, which can perform such kind of glue-like behavior or the gating mechanism. They working together, which have the same performance like the LSTM with FPTT. So this is a reason, but there is no specific learning rules for the LTC neurons. You're just using the BP, the magic of the autograde. Yeah.
Okay, and we have one last question by Michele Nardin. Can you extend FPTT to other spiking neuron models beyond LEAF?
Yeah, I mean that's
I guess you can. No, it's a generic algorithm.
Yeah. So that in our experiment on the DVS-gesture datasets, we applied using convolutional neuron and Huxing-Huxel models, which are hard to train before. Within our FPTT, now we can train them to achieve quite a decent number, but with much more biological realistic neuron types. So we think that because the computer graph is much more clear, it's robust to the gradient calculation. So maybe we can use more biological realistic neurons within FPTT. And yeah, the answer is yes. Yeah.
Okay, so short answer is yes. Good. Yeah. Well, thanks again, Bojian, and I think it's time to stop. So now we have a a 15 minutes break, I think, and then we have a Zoom meeting for the General Assembly.
Yeah, exactly. Do everyone please come along to that. I'm just going to put that in the chat, basically just to talk about what we can do in this community and maybe how we can make things better, ideas for future meetings and things like that. And if you don't want to come along to that, there is also the next session of talks, which is a little bit later than that. All right. Thanks, everyone.
Okay.
See you in 15 minutes.
Thanks to all the speakers, and see you soon on Zoom.
Thanks, Tim.